she's from Radio Shack in about 30 years ago, so, can't complain much. Yes, let's begin. Dear Heavenly Father, we thank you for today. I thank you again for this class, for these students who may be with us today. Help us to glorify you, Lord, in what we do this day. In your name I pray, Lord Jesus. Amen. Okay, so last class, of course, I did some bad things, and I think the worst among them for you guys was I think I indicated that if the modulus of the function is unbounded, there was a one-to-one correspondence between the modulus being unbounded as you approach z naught and the function either having an essential singularity or having a pole of order n. That's simply not the case. If it has an essential singularity, the limit of the modulus as you approach the limit point simply doesn't exist, because there's some directions where the modulus will be finite. There's other directions where the modulus will be infinite. And there's a very, very rich structure to the essential singularity. All kinds of crazy stuff happens near an essential singularity. The modulus isn't even bounded. The limit of the modulus doesn't exist. It's worse. So if the limit of the modulus exists and is infinity, what that means is that for any possible direction as you're approaching the point, the modulus gets as large as you want if you get close enough, right? It just keeps being bigger and bigger and bigger in all possible directions. That's not the case for an essential singularity. But it is the case for a pole of order n, and that's the theorem that's in the notes. All right, so that was the thing. I felt like I should stop and say a minute or two about that. Now, that was one thing I forgot to say. But there's something worse that I forgot to say last time, and I need to address that before we go on. It's very important. It's one of the more important things I'll do in this course. All right, so let me get to that just a second here. So here's how it goes. A Russian physicist, a Polish janitor, and a rabbi are on a plane. All right, and suddenly the pilot has a heart attack, and then the co-pilot has a stroke, and there's no one to pilot the plane. And then people are like, who can fly this plane? And the Russian physicist is like, I am a theoretical physicist. I do not know how to fly a plane. I do numbers. I can't do, it's not something I want to do. It's the work of an experimentalist. I leave it to someone else must do this. I'd rather die than pilot this plane. And the rabbi says, it's Saturday. I can't get out of the seat. Oh well. And then so it comes to the last person on the plane, the Polish janitor, and he says, But I'm just a simple pole in a complex plane. Okay, there you go. Congratulations, you are now part of the 0.005% of the population who can understand this joke. So, very good. There are different ways of delivering this joke. It may be more or less politically incorrect, but anyway, that's a relatively tame version of it. I'll stand by it. All right. So that's the greatest shame Monday is that I didn't tell you that. Because that's when it was supposed to happen last lecture. It's just sorry about that. Okay, so partial fractions decomposition. I think I heard that in my complex analysis class, and I try to pass it on to each one I teach. Partial fractions decomposition. So the other thing I forgot to tell you last time, which is very important, is the definition of meromorphic. F is meromorphic. On U, let's say a subset of the complex plane, possibly the extended complex plane, okay? So we can also talk about infinity. Is meromorphic on mu if F is holomorphic on U except at isolated singular points. or another way I could say this is f is meromorphic if all of its singular points are isolated. Okay. So if we think about what does a rational function look like, right? What does a rational function look like? F of z is p of z over q of z, let's say, right? Now, what's the deal? If this is an improper rational function, that means the degree of the numerator is larger than the degree of the denominator, or could possibly equal. You do what? You do long division, right? You peel off a polynomial piece. So we know this from our youth. So let's say that there's a polynomial piece. Let's call it, I don't know, whatever you want. R. Well, no, R is a bad choice. How about h of z? I don't know, whatever we'll call it. H of z, the polynomial piece, plus r of z divided by q of z, right? R is the remainder in the long division. And so the what you have there is two pieces, right? And so this is something like, you know, a naught plus a1z plus da 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 plus a n z to the n for some finite n, right? And this q of z, it can factor. Without loss of generality, think of it as monic. Put the if there's a leading coefficient of q, you can put it up in r, whatever. So something like z minus z1 times to the to some power, and z minus z2 to some power. Da da da. Z minus zk to some power, right? It's a complex polynomial, though, right? It completely factors fundamental theorem of algebra. Hey, we've proved that. So what's the deal? This piece, so it's like, this is, r of z, like that, right? So at infinity, so let's talk about this. This is an entire function, right? Meaning that it's holomorphic on C, right? But it's not analytic where? Infinity, right? That term is singular at infinity, right? Because it corresponds to a pole of order n, in fact, for the reciprocal function at 0. So that's actually a pole of order n at infinity. And certainly that's an isolated point as well. The singularity at infinity for h of z is an isolated point in our definitions. And on the other hand, this is holomorphic, right? This is in basically the set of holomorphic functions on C minus what? With what? The points z1, z2, da da da, zk removed, right? So that piece is holomorphic on the entire complex plane modulo those points where the denominator is 0. And that's also what? That's analytic at infinity, in fact. This is, So this is an arbitrary rational function, right? Completely arbitrary rational function. And I've just argued for you that every singular point of it is isolated. It's either the singular point infinity, or you have the singular points where the denominator is 0. Anyway, those are there's not infinitely many of them, right? So they can't be they can be isolated, right? If you have a finite set of points, you can isolate them, unless the points are not distinct, in which case we just call them the same point and stop being stupid in our labeling, right? Any questions? So every rational function is meromorphic. But the interesting thing is the converse is also true. In fact, a meromorphic function on the extended complex plane is a rational function. So this is denoted C star. In my notes. So theorem, a meromorphic function on the extended complex plane is a rational function. So the proof, well, this direction was the example we just did, right? How about the other direction? So we should let f of z be a meromorphic function on the extended complex plane, right? Which means what? All its singular points are isolated, right? It could have infinitely many singular points. That's allowed. But they have to be isolated. All right? Excuse me. All right, so if f is analytic at infinity, then we define, so a couple cases here. Case one, if f is analytic at infinity, all right, if f is holomorphic at infinity, then define p of infinity. I'm defining this new function p sub infinity. So p sub infinity, what? Oh, okay, fine. P sub infinity of z is equal to f of infinity. I wanted it to be something else. I'm just being silly. Because if f is holomorphic at infinity, that means the value of f at infinity is defined. All right. 2, otherwise, f has a pole of order n, right, at infinity. Oh, I think I've slightly, I think I didn't quite capture the definition of meromorphic yet, did I? What did I leave out? It looks like I've got something to prove here, but I don't. Why is that? What is the complete description of meromorphic? If f is analytic on D, except possibly at isolated singularities, each of which is a pole. What's a pole? Quote unquote. Which are poles. In other words, they're poles of order n. Okay, so there's no essential singularities either. It is forbidden. Otherwise, f has a pole of order n at infinity, right? And then what? And then, p infinity of z is polynomial of order n. Now, I think this p sub infinity, it refers to a discussion we had in the previous section where I expanded, I looked at the expansion of f about infinity. The principal part of that expansion is called p sub infinity. It's the polynomial piece of the Laurent expansion on the exterior annulus at infinity. Okay, so in other words, the definition is like f of z is equal to p sub infinity of z plus like, a minus 1 over z plus a minus 2 over z squared, so forth and so on. So this was the principal part at infinity. Which is a polynomial. Okay. Now, okay, so what? So check this out. if you look then at the function in both cases 1 and 2, what can we say about f of z minus p infinity of z? What's the deal with this function? Basically, you're subtracting off the part which is the principal part at infinity, right? So what you're left with, and this is generically a trick that we can do, if we take a function that has a Laurent expansion and we subtract the principal part off, what we're left with is just the analytic piece. We're left with the piece which is just a power series, or here, reciprocal series, because we're talking about infinity, which is kind of, mirrored everything. It's kind of flipped over. But anyway, this is analytic, right? At infinity. Moreover, what can you say? What happens to it? What is f of z minus p infinity of z? It goes to what? It goes to 0 as z goes to infinity, right? Because the only piece which is non-trivial at infinity is the principal part, and you're subtracting off the principal part as you go to infinity, so it just leaves you with 0, right? This piece at infinity, all these terms, they go to 0 at infinity, and what you're left with is just this piece, but you're subtracting that, so you just get 0. So what? So then, if we label the poles, so we assume that this is a meromorphic function, right? So you've got poles z1, z2, zk. Suppose that these are the poles of f of z in C, all right? So not infinity, but the poles at particular complex points. Well, you can also consider the principal part of the function at each one of those poles, right? And so, like, let's say that the principal part at the kth one is denoted p sub k of z, right? So that would be something like a sum. It depends on what the order is. Let's say j equals 1 to n sub k, and so I don't know. I need some sort of stupid notation here. A sub kj over z minus zk to the j power, right? So that goes from -1 all the way up to n sub k, right? This is basically a sub k 1 over z minus zk plus plus a sub k n sub k over z minus zk to the nk power. This is the principal part. Suppose that this is the principal part of f of z at that pole, all right? So what happens if you look at f of z minus p sub k of z? This is what? This is going to be one of the holomorphic functions at zk, right? So these are the offending terms. These are the singular terms, let's say, at that pole. That's what's making f infinite there. So if you subtract that, you're left with something which is just holomorphic. And we can do this for each pole, right? So you've got a piece of k, a principal part at each of the poles, k equals 1 to however many there are. I shouldn't use k as the, I forget what's my counting here. I said that there are m poles, so here's the mth pole, all right? Okay, finally. What do we have? So we can look at g of z. With all of this in mind, we construct g of z. What's g of z going to be? G of z is going to be equal to f of z, all right, minus p infinity of z, minus the sum, k equals 1 to m, of p sub k of z. So what can we say about g of z? Is g of z analytic at infinity? Yes, because, I've removed, this is the part which would make it not analytic at infinity, right? We subtracted it off. And so what happens, and also what's the limit as, g of z goes to what as z goes to, it goes to 0 as z goes to infinity, right? Also, because this minus that goes to 0, and this is a sum of reciprocal terms, all of which vanish at infinity. Where else is this function analytic? All of the complex plane. See, wherever there was a pole in F, what have we done? We've subtracted the piece which is infinite, right? So what is G? So G of Z is holomorphic on the complex plane, right? And it has limit 0 at infinity. It follows that G is bounded. It is a bounded entire function. And what do we have? What do we have? Remember Liouville's theorem? Yeah, g of z is equal to a constant. But that constant must be equal to 0 because of this, right? And what does it mean if that constant is 0? That means that f of z is just equal to p infinity of z plus a sum k equals 1 to m of p sub k of z. And what is that? That, my friends, is a rational function. Sum of a polynomial and a sum of reciprocals expanded around the poles, right? This is a rational function. So that proves then that any meromorphic function on the extended plane is a rational function. Very, I love this argument. I think it's very interesting, right? Now, it doesn't really help you. Well, it kind of helps you. I guess it doesn't help you too much with how you actually calculate these partial fraction decompositions, right? But maybe you already remember that from calculus 2. How do we find partial fractal decompositions of functions, of rational functions? What are the rules? Do you remember? No one remembers? As unfortunate. Yes, equating coefficients. Yeah, setting things equal to 0. Let me refresh you guys' memory a little bit. Look at an example or two. There's one example in the notes here which really spans about a page and a half, maybe 2 pages. And if you really understand that example, it has most of the major calculational techniques in this little part of the course, which is actually, it's an important part of the course because many of our favorite examples come from this technique. Some partial fractions, like just.
There was an example in the notes that.
Oh, yeah, I'm going to show it. I don't have it memorized. Let's see here. Yeah, come on. Hey. Oh, yeah. My computer overheated yesterday. I tried to upload too many videos at once. So then all my, I usually leave the complex notes open, you know. All right, come on. You can do it. You can do it. All right. Actually, I think this is a really nice example. I have a couple basic examples in here. Come on. All right, here's a warm-up example, kind of a standard thing, you know. So I have a cubic over a quadratic. So like your first order of business is do long division or whatever floats your boat to get a polynomial plus a proper rational function, right? Then you need to factor the denominator, which is z plus I times z minus I, and then we know we should look for that. By essentially the proof of the theorem, right? Proof of the theorem says you just look at sums of the terms that have poles, right? I mean, that's anyway. So that'll work, and multiply, and then if you plug in z equals to I and z equals to minus I, it will peel off A and B for you, right? The case of distinct roots is it's a nice case, right? So there it is. The proof is in the algebra ultimately, and of course so partial fractions in some senses reverse common denominatoring. So if you make a common denominator of these two things, you'll get back where you started, and that ultimately proves that what I did was correct, right? I mean, I suppose in principle I could write down a partial fractions decomposition that wasn't right? And then if I try to do the algebra, I'll get nonsensical algebra, right? I'll get 0 equals 1 and other such things. So I'm not going to try to fully prove that the templates I'm writing down are sufficient. I mean, the proof is in the working out. Okay, so anyway, this one is a little bit more interesting. This is the example I was talking about. Example 6.45, I've got 1 plus z over z to the fourth minus 3z cubed plus 3z squared minus z. All right. So this one, you can factor out a z, and then you're left with z times z minus 1 cubed. All right. So in that case, the partial fractions decomposition is a over z for the z, plus b over z minus 1, plus c over z minus 1 squared, plus d over z minus 1 cubed. And anytime you have a particular factor that's repeated, then the algebra gets nastier. But I want to show you a new, maybe, I don't know if you've seen this before, a technique to sort through how to find A, B, C, D that's a little bit, maybe you haven't seen this before, I don't know. So the first order of business, of course, is to clear out the denominators by multiplying by the denominator of the left-hand side, right? And then that leaves me with 1 plus c, a times z minus 1 cubed, and so forth, right? And then it's convenient for my purposes to actually multiply these out for the steps that follow below. Maybe it isn't, maybe it is not. I mean, I multiplied it out. Maybe you could get away with not multiplying it out, but it's just easier. Okay, so then what I do is I differentiate. This relation holds for all z, right? So you can differentiate it. And differentiating will lower the order of the terms, right? And so once differentiating gives me this identity, twice differentiating gives me that identity, thrice differentiating gets me to here, at which point I'm like, hey, I like that equation. That tells me a is equal to minus b. And then you just kind of work your way back up. Did you do this in calculus too? No, you did not. I don't know. There must be people who teach this in Calc 2 somewhere, but I haven't. If I was teaching this at the same time I was teaching Calc 2, I might be tempted. it would be at my mind. It'd be tempting not to. But you remember, though, that, of course, the repeated root case is the nasty case. So here's a way to get through the repeated root case without too much trouble. So a equals minus b, but then if you go back to then this one, if we put z equals to 1, that's a good move because what? Oh, I'm sorry, in star. Then I go back. Actually, I go from here, then I go back to star because that's easy. If I put z equal to 1 here, it kills this, and that, and I just left with d, right? So that gives me d equals to 2, right? I mean, what I'm using is a sort of hybrid approach. I'm looking for whatever equations are easiest to like just extract a constant from. Basically, I'm not. So again, that gives me d equals to 2. If I put d equals to 1 in the derivative, then what goes away in the? It should be this is gone. I think we only should be left with the c and the d terms. That's easy to see. Maybe that's a reason to not multiply this out. If you didn't multiply this out, when you differentiate this, the next one would be like 3z minus 1 squared, right? And this would be twice z minus 1. I mean, when you have to do the product rule is the thing. But both of the terms in the product rule would have a z minus 1 left on them. This is the only term that would differentiate. I mean, this would differentiate to like cz. And then there's another term that still has a z minus 1. Anything that has a z minus 1, when you evaluate at 1, those terms drop out, right? So that would be a reason for not multiplying it out, because then you could easily see when you plug in z equals to 1 into the derivative equation, like which terms are just dropping out, right? But anyway, if you put z equals to 1 in the derivative equation, that gives you an equation that just involves c, and that tells you what c is. And then finally, I put z equals to 1 in the second derivative of the condition. And after the dust settles, we have this partial fractions decomposition. I mean, partial fractions of anything interesting, it takes some work, right? But it's work that you can do. I mean, for me, it's a happy place. It's just polynomial algebra, right? Here it is. And so this function is meromorphic because it's rational. And in fact, it's analytic at infinity. It has no polynomial piece, right? And its poles are, it has two simple poles. Oh, no, excuse me. It has two poles. One is simple. Z equals 0 is a simple pole. Z equals 1 is a pole of order what? 3, right? So now I would like to connect the concept of partial fractions with that of the Laurent series, right? So the other thing I failed to emphasize last time with the Laurent series expansion was, we had that formula a sub k z minus z naught to the k from k equals minus infinity to infinity, right? And we learned that the kth coefficient is captured in terms of a particular integral of the function divided by the power function, right? Integrated over a circle in the annulus on which the Laurent series is defined. What I kind of indicated was, and again, I'm not posting this to YouTube because of the awfulness of it, but I think I had in my mind that you could evaluate the derivatives of the function at the center point to figure out what the coefficients are. But of course not. I mean, the whole point of the Laurent expansion is that the function need not even be defined at the center. The function can be infinity at the center point. Those integrals are still well defined. The integral around the circle inside the annulus that we're studying is still defined. So those integral formulas are more general than the differentiation formulas in that sense, right? So that's just a word of caution. Careful, you can only say a sub n is the nth derivative at z naught divided by n factorial if the function's actually analytic at z naught. If that's not the case, you can't do it. Okay, so there's really two interesting points to study annuli around for this example. You can study the annulus that's centered at 0, right? Or you can study annuli that are centered at 1. Those are your two poles, right? And anywhere else, the function is analytic, right? So if you study the Laurent expansion around any other point except for these two, what you're going to get is just a power series that's radius of convergence extends to either 0 or 1, whichever one it hits first. So the two interesting cases are z equals 0 and z equals 1. At z equals 0, look at it. Well, I guess I started with z equals 1 because that's easier. Z equals 1, check it out. These are already expanded around 1. So all you got to do is fix this 1 over z, which is analytic at 1, right? So how do you rewrite that as power series at 1? Well, you use the recentering trick. Minus 1 over z is 1 plus z minus 1. That's geometric. And there it is. So there is the analytic piece, the f sub 0 in the Laurent decomposition we talked about Monday. And there you have it. That's the Laurent series. As you can see, it has a principal, has a pole of order 3, right? At z equals to 1, and there's the Laurent expansion. As you can see, knowing the partial fractions decomposition, it's easy to get to the Laurent decomposition just by a simple geometric series argument, right? All right. Now the other singular point is 0. That's a pain. I mean, the difficulty turns over, right? This is already centered at 0, and these are not. Right? So then I need to expand those analytic functions at 0 as power series. This brings us back to essentially calculus 2 techniques again, because I can use what? I can use a geometric series approach again. So this one to start with, 1 over z minus 1 is minus 1 over 1 minus z, which is that by geometric series result. How do you get to 1 over z minus 1 squared? Well, that's the integral of 1 over z minus 1. So we can integrate, of course, this geometric, so we can differentiate this geometric series to get back to g again. And so we use, we integrate and differentiate geometric series to get to and from, just the 1 over a reciprocal function to a 1 over something squared function and so forth. So this is the standard calculus 2 trick, right? But then this gives me sum j equals 0 to minus j equals 0 to infinity minus j plus 1 z to the j. That is the power series for 1 over minus 1 over z minus 1 squared. And then I have to do what? I have to do 2 integrations to get this z cubed. Every time I integrate, it raises the power by 1, right? Integrate once, 1 over square. Integrate twice, 1 over reciprocal. Once you get to the reciprocal type function, it's geometric. By a geometric series, convert it to a series. I integrate it twice to get back where I started. I differentiate twice. And out pops the power series for that. I hope this isn't the first time you're hearing this story. This definitely should have been presented to you in Calculus 2. If it was not presented to you in Calculus 2, with x's, of course, you were robbed. All right. Anyway, so once you put that all together, you have f of z is equal to minus 1 over z plus this stuff. And it looks like this. Minus 1 over z plus 4 plus 9z plus 16z squared, and so forth and so on. Right. Which, at first glance, might make you think that this is not analytic at infinity, right? Wouldn't you be tempted to say it's got an essential 0 at infinity? But you'd be wrong, right? Because these actually just represent those 1 over z minus 1 plus 1 over z minus 1 squared plus 1 over z minus 1 cubed. I'm forgetting plus minuses, but these are actually just the series that represents the sum of the over z minus 1 functions, right? And those do tend to 0 at infinity. So there's some, anyway, so any questions about this? I mean, I know there's a lot into this example is my point, right? You got this new idea that we can differentiate relations to go through the partial fractions algebra faster or more efficiently. We use geometric series technique to recenter a given reciprocal function. And also we integrate and differentiate series to get, get more than just reciprocal functions, right? We can do anything over like a z minus. If I had 1 over z minus 1 to the 4th, I would need to integrate 3 times. Geometric series, then differentiate 3 times to get back where I started. I mean, this, yeah. And that brings us to chapter 7. Here's some sobering comments at the start of chapter 7. The residue calculus. Let's get into it. So, chapter 6 is really about sort of trying to provide a home for the calculations in chapter 7. Chapter 7 is actually how we do things in this course, at least. I mean, chapter 6 is necessary, but it doesn't really, the partial fractions is still as good as it gets for that part of the material, right? That's very computational. But the other results in chapter 6 I wouldn't really categorize as very efficient computational ideas. This chapter is very, very computational. You guys will like this. Most of you like computations. But these, on the other hand, these are worrying comments, very worrying quotes if you consider their source. Ramir. Okay, you got to understand, Ramir is, he is a master of complex analysis. This guy did really, really deep work in analytic function theory in the 20th century, right? And this is what he says. Nevertheless, there is no canonical method of finding for a given integrand and interval of integration the best path in the complex plane to use. This man has done nothing in his life but study complex analysis, and this is what he says. This is not the opinion of an ignorant person. From Alfors, who wrote the central text of complex analysis, all right? That is the go-to book. Most other complex books you read written nowadays, you will find that as one of the motivating texts for the author, all right? Even a complete mastery does not guarantee success. So I'm telling you this, as you work on your homework, if you can't figure it out, you shouldn't feel too bad. Right? You got good company. I'm just joking mostly. The problems I'll assign you in homework and we'll look at in here are much easier than what they're talking about. The point is that this method is open-ended, and there are very much more complicated versions of what I'm going to show you in this chapter. By the way, Ron Gordon? Yeah, Ron Gordon is well known for, somebody will post this seemingly impossible integral, and then a couple hours later he just posts his solution. This just makes you go, how? But he likes his stuff. Anyway, just the wonderful thing is with the stack exchange, we have so many examples to work off of. All right, there are 4 rules. 4 rules. Well, first of all, what's the residue theorem? What is a residue? I guess I should put this away. Thank you. Oh. So we are dangerously close to solving calculus problems a really, really new way. Hopefully that'll happen Friday, okay? We just have a little bit more background here. So a residue is really just a very specialized notation to pick at the -1 coefficient in the Laurent series. So if you have f of z is equal to a sum, say n equals -infinity to infinity of a sub n z minus z naught to the n. So, we're thinking rho less than, you have some annulus. This is the Laurent decomposition, the Laurent series for the function on that annulus. We remember we have that the coefficients, the nth coefficient is what? It's 1 over 2 pi I integral over a circle of radius r. This is some circle in the annulus. Doesn't really matter which one. F of z, because the deformation theorem says that we can deform to another circle in the annulus at no cost to the integral because the function's holomorphic in the annulus. Right. So that's again, I can't evaluate at z naught because I don't even know if f of z naught's defined. That's what makes these Laurent series so clever. You have a Laurent series expansion for a function about a point which the function may not even be defined at that point. In fact, usually, for it to be interesting, it's not. It captures the infinite nature of the function at that singular point in the most interesting way possible. But anyway, the residue of, and there's different notations in different books. Here's the most annoying, cumbersome notation possible. Residue, I guess I could make it worse. Here, residue, spell it all out. There we go. That'd be the most clumsy notation possible. Equals to a minus 1. It's just the minus 1 coefficient. Now, this is going to get old really fast, so probably with something more like res f of z, z naught. All right. Now, what's the significance of this? The significance of this is that a minus 1 is, what is it? It's 1 over 2 pi I, the integral of f of z dz around a circle in the annulus of definition of the Laurent series. This single coefficient tells you how to do integrals. That's amazing. Because how do we find Laurent series? Well, we don't have to integrate to find a Laurent series, right? We can use other things. A known series for sine, right? Some kind of substitution with a Taylor formula or a geometric series argument, partial fractions. All these things don't involve integration, and yet they allow us to find integrals. That's whack. So some example. The residue of 1 over z minus z naught with respect to z naught at z naught is what? Excuse me. All right, so first one's easy. What's this? That is, what's the Laurent expansion of 1 over z minus z naught at z naught? This is the residue is 1. This is its own stupid Laurent expansion, right? This is like, kind of like implicitly this question is asking, what's the Taylor polynomial of a polynomial? Like, well, it's the polynomial again, especially if it's already centered where you want it. These are already centered where we want them. This has no minus 1 piece. So the answer is 0. It goes back to that fundamental behavior that we observed much earlier in the course. Remember, we integrate the power z minus z naught to the k around a circle. We only get non-trivial in the case that it's the reciprocal power. Everything else integrates to 0. This is the mathematics which exposes that for what it is. All right? What's the residue? Now, there's two interesting residues to ask about here. The residue of f of z at minus I, and the residue of f of z at I. Unfortunately, it's kind of like the contrast of I didn't. Oh, wait a minute. No. It was z minus. It is more interesting than that. This was equal to z minus. It's something lost in my copying. It was z minus this. All right. Now it's more interesting. So if you look at this, the principal part of the Laurent expansion at around z equals minus I is this piece right here, right? So this would be like the f1 of z, whereas this piece and this piece together are the f naught of z. With respect to the center, z naught equals 2 minus I. See, because this piece and that piece are analytic. They're analytic at minus I, whereas 1 over z plus I is not analytic. In fact, that piece of the function is not defined at minus I. But it's singular in the reciprocal sense, right? I mean, that is, and so there it is. This is the piece which would give you the principal part of the Laurent expansion. These we could expand into Taylor series about minus I, but you don't need to. Once you have this, you can read from that directly that the residue is what? Negative 1 over 2I, right. And how about the other one? What's principal now is different. So this piece is the, let's say, G naught of z, whereas all of this here would be G1 rather, and this would be the G naught of z. This is the part which is an element. This is holomorphic at I. This is not holomorphic at I, right? That's singular at I. That's the principal part of the Laurent expansion centered about I, and so this gives me 1 over 2I. I mean, I guess if I wanted to convince you entirely, I would find the whole stupid Laurent expansion centered at plus or minus I respectively, right? I'm just not going into that because I claim what's going to happen is when we go through all the details, all that's going to happen is the G sub naught and the F sub naught pieces are just going to give you a Taylor series in plus or minus I respective, and that doesn't contribute to the residue. Now, this kind of thinking we'd like to formalize, and that's what we'll do next time with the rules 1, 2, 3, and 4. These 4 rules are the bread and butter of calculating residues, which is actually it actually turns out to be pretty easy. In fact, the great news, folks, is that most of the time I don't even need to calculate the whole Laurent series because I want to have like a laser focus on finding just the residues at the poles. And then these residues at the different poles paired with Cauchy's residue theorem will allow us to calculate integrals just in terms of whether or not there are infinities inside the contour of integration. That's where we're going next time. So thanks, guys. I will shut up.